Alright guys, we are back with another video. This time we want to partition a linked list. So we want to partition a linked list around a single node. Alright, so what we want to do is to first get a linked list. So let's say, for example, our function gets a linked list like 2, 3, 7, 5, 4, 3, and how about 6? Alright, so this is the linked list that our function gets, and it will get a node alongside this linked list as well. So that node would be our partition node. So here it would be 5 for us. And so this is our partition. And what we essentially want to do and what we want to get as an output after running this to our function is to have all the nodes that are smaller than partition on the left side. So 2, 3, and 4, and 3. And then all the nodes that are equal to or greater than partition on the right side. So here would be 6, 7, 5, and yeah, that's it. So what we are essentially doing is we are kind of sorting the linked list halfway. And here's the part where the linked list is partitioned. So there is a left partition and there is a right partition. And it doesn't matter where our partition element ends up in. So it doesn't matter if it's exactly in the middle or if it's somewhere else. Also, the same applies for every other node. So we don't care about their order. So in this output, we preserved their original order, but it didn't matter. It didn't make any difference if we had 6 and 7 like this. So this still would be a valid input. So we don't care about the orders. We only care about whether every element after the partition is equal to or greater than the partition. So these are all equal to or greater than 5, and these are all less than 5, right? Which is our partition. Now, how are we going to do this? Where there are multiple methods to approach this. One is to basically create a new linked list and to go over each element in the input linked list and then see if it is how it compares to our partition node. And if it's the same, if it's smaller than the partition, we would append it to the new linked list. If it's not, then we will wait for the second pass to go over this linked list and then add it then. So for example, now if we run through this linked list, we can skip 6 because it's greater than or equal to 5. When we reach 2, we will add it as a new node for our new linked list. When we reach 3, we will add that to our linked list as well. When we reach 7, we will skip it. 5, we will skip it. 4, we will add that to our linked list. And 3, we will add that to our linked list as well. And whatever node, and now in the second pass, after detecting this null in the end, we will start the second pass, and on the second pass we will only append the nodes that are greater than or equal to. So again, we will run through the linked list. 6, 2 is less than 5, we will skip it. 3 is less than 5, 7 is greater than 5, we will add it. 5 is equal to 5, so we will add it, and that's it. So this is one way to approach it, but as you can see, it's not very efficient. So we want to write an algorithm that is even more efficient than this. So the other way to do this is to go over this linked list, and like, for example, at first node, when you detect that it's small, bigger than or equal to 5, we will write it down, but we will append it to the end of our linked list. So let me explain. So we will write down 6. So maybe I should write it down in the middle. And we will go through the rest of the elements. So 2 is less than 5. So what we are going to do is to append it to the before the 6. So we will say that this is our head, and we will set the dot next our new node to be the head, the previous head. So we are basically, if it's our linked list, if this is a view of our linked list, and this is head and this is tail, we are basically changing the head by appending something new to the beginning, by basically adding something new to the beginning of our linked list. So we will create a new head, and we will point it to the previous head, and this is no longer the head. So this is different than adding something to the end of the linked list. So when you want to add something to the end of the linked list, you will update this next pointer from pointing to null to pointing to your new node, and then that would be your new tail, and this would be the one that points to null, and yeah, it will change your tail. So we can basically do this. So we can say 2 is the new head, so this is no longer our head, and we can get rid of this as well. And we will continue traversing through this linked list. So 3 is smaller than 5, so this will get added to the beginning again. 7 is bigger than 5, so it will be added to the end of the list. 5 is equal to 5, so it will be added to the end, and 4 is smaller, so it will get added to the beginning. 3 is smaller, it will get added to the beginning as well. So this would be our resulted linked list. As you can see, the order is not preserved here, but that's okay, as we said in the problem statement. This is another way to approach it, and for this way we are having, for the runtime, we are having O of n, because we are going through each element in our linked list once. And for the space complexity, so for space, we are also having O of n, because we are basically creating a duplicate off of our linked list. We can also approach it in other ways. Like, the one other way that we can approach it is to edit this linked list in place, but that wouldn't be that safe. Basically, what we can do is to go over this linked list. Let me write it down somewhere else. So if we say 6, 2, 3, 7, 5, 4, 3, what we can do is to, while we are going through each element, like we are saying 6, so 6 is bigger than 5, we will skip it because we basically have access to the head because the head is given to us, but we don't have access to the tail. So what our option is to add something to the beginning of the linked list if we want to edit this in place. So 6, we can't move 6 to the end of our linked list just yet because we don't know how long is our linked list. So 6, we will skip it. 2 is smaller than 5, and we can actually append it to the beginning of our linked list. So we can say that this is 2 now, and this is our new head. Suppose that we have a variable somewhere that stores the head. It was previously pointing to 6, and now it's pointing to 2. And we can say that and then we need to remove 6 from here. But since we have one pointer at a time, we actually don't have access to 6 anymore to really be able to remove 2 and point to its next node. So what we can do is to use the trick that we learned from the previous example. If you haven't checked out that video, please go check that out, or I explain this method thoroughly. But basically what we do in this method is to keep the place of this node in address, but remove its value and replace it with the value of the next node, and we will keep the value of its pointer as well, or sorry, get the value of the pointer of the next node of its next node as well, and put it in place of the value of our current pointer. And basically when we do this, this will become the new 3 node. So if I clean this up, this will become our new 3 node, and this will point to 7. And so there is no longer anything pointing to the node that its place is here in memory. So this node and its pointer will get lost in the memory as they are not part of this linked list. And basically we have a copy of its value here, but this node itself still exists but gets lost in the memory. So as far as I know, the garbage collector of Java will come after it and remove it after a while that it's not being used. So 3 and then 7. So we removed 2 basically here. So now we are pointing at 3. So again, we want to do the same thing. So 3 is smaller than 5, so we will add it here. And then what we do is to grab the value of 7 and put it here. So this is now 7. And we will grab its pointer as well. So this is our new pointer. And basically these two also get lost in the memory. And this pointer also is no longer valid. It's overwritten by the green pointer. And now what we do is to check 7, and 7 is greater than 5, so we keep it here. We now go to the next node. So we were here all the time, so we will now go to the next node, and our header is our head now points to, let me write it this way. Our head now points to this node. So 5 stays here, and 4, and then we move to 4. 4 is smaller than 5, so we remove it from here by assigning the value of 3 to it, and assigning the pointer of 3, which is pointing to null, to it, and then moving it back to the beginning. So now if we were to define our new head, this is our new head. And again, we will read the value of 3. So 3 is smaller than 5. So we will basically move that to the beginning as well, and replace its value or address in memory with null. So now 5 itself is the last node, and basically we can remove this pointer and not show it in our diagram anymore, just to be consistent with the previous drawings. So our resulted linked list is something like this: 3 4 3 2 6 7 5, which is the same as the result from the previous node. But as you can see, this gets way more complex, but the runtime of this is still O of n, and the space complexity of this is now O of 1, because we aren't using any additional space. We have constant use of space, and we are using whatever space that's given to us. But this method is a little bit more risky in that you might end up modifying, your function might fail. Like, there might be a string passed into your linked list, or there might be something in your linked list that your function is unable to evaluate, and whenever your function returns at that state, your linked list is already modified, and you lose your initial linked list altogether. So I would say this method is much better and much simpler to implement. So I would say we should go with this method, right? So let's go with this method. We will generate a new linked list and we will return it. So let's go back to our code editor. So this is our code editor, and this was a linked list that we previously created. So I'm going to change some of its values. Maybe this one would be 4, right? And run this again. So this is our new linked list. Now what I want to do is to create a new function over here. So I'm going to call it, this will return a linked list node, by the way. And I will call this one partition, just partition. And it will get a linked list node, which will be our head, and the linked list node, or do we want a linked list node? We want the value of that node, right? Just to make that comparison. Well, it's up to us. We can get the node and then read its data, or ask for the data of the node itself. But if we are passed in a data, then we don't know if that's from a node or not. But does that matter? I would say no, because this algorithm would work whether the 5 is one of our nodes or not. So I would say we can just ask for an integer and call it our partition, right? Now let's go to the body of our function. So we want to create that new linked list node, and we will probably call it partitioned linked list, right? All right, let's call it that, and let's return that at the end. Partitioned linked list. So what is it saying? It's saying that it's not initialized, which is okay. So now, what should we do? Well, I think we can now So what did we do here? We basically looked at each element in our linked list. So let's do that first. So I can say, since this is a linked list and we don't know how many elements are inside this, we will use a while loop. And I can basically create two more nodes here and call them current node and assign it to head for now. And do I need a runner node? I don't think so. So I can say while current node itself is not null, right? Do this loop, and at the end of each iteration, just go to the next node. And all right. So that's great. Now let's see. So we want to read the value of current node. So current node.data. And we want to create a conditional statement here. So if this data was less than the partition, right? What do we want to do then? If it was less than the partition, we would want to append the node or add the node to the beginning of our new linked list. So maybe I should say this is partitioned list head, right? Partitioned list head. And so I'm going to say if a value is less than that, we would say partitioned list head is now that node, right? So we are basically moving the head, but before doing that, we will probably want to say, well, this is where it gets tricky. Let's think about it. So what we are saying is that if this node has a value which is less than the partition, we would want to move it to the beginning of our linked list, right? So what we want to do is to first move this to the beginning, right? So this will be our new head. But what will it point to? Will it, because we don't have any references to the previous head anymore. So how are we going to make that connection? So maybe we should create a new node as soon as we do that. So maybe the way to deal with this is to say, is to create another node and call it previous partitioned head, and call this current partitioned head. And the current head of that linked list is really, I think, null, right? That is null. And the previous head, or the previous head is null, and the current head is the same as previous head. Can we make that statement? I'm going to assign them both to null for now. So now I'm going to say we want the current partitioned head to be returned. Now, if this data is less than partition, we want to say that current partitioned head is current node, but current partitioned head dot next is previous partitioned head, and we want to say that previous partitioned head is now the current partitioned head just after we do this. So I can maybe rename this to just previous head and current head. Okay, good. Now, else, what happens if this is not the case? If this is not the case, what we want to do is to just add the nodes that are greater than or equal to the partition to the end of our linked list. So what we should do in that case is to say current head dot next is current node, right? Is current node, and I think I figured out an issue, but I'll see if that's a big deal in a bit. So and that issue is that current node is like a package that has both the data of the node and the pointer of the node. So when we put it inside this, we are basically storing the value of the pointer to the next node in it as well. And that could be basically the rest of the linked list in itself. But the good thing here is that we are overriding that pointer that we just assigned to this in the next line, on line 14, and so that won't become a big issue for this. But for this one here, so we are assigning it to this node, and what we have to do after that, I think let's see. Okay, so we have a problem. We need also to have access to the tail. Alright, so let's create another one. Linked list node current tail. It's set to no. So what we want to do is to say current tail is current node if it's greater than the partition. So this is the else statement. And we will probably only want to... Alright, so if we do this, this is our current tail, and we will also probably need previous tail here. Linked list node previous tail is no. So current tail is that, and we will say that previous tail dot next should point to current tail, and previous tail should get updated to the current tail. And this time we are not overriding the pointer of current tail, so I'm a little bit scared here. So what happens now is that at the end, let's say we add two items to this. Like, let's say we add 6 here, so 6 will become our current tail, which points to other nodes. Like 6 now points to 4. And then let's say that previous tail was null, so null is now pointing to current tail, which is this. And then the previous tail, which is pointing to this node, is the node itself. What are we doing? So the node itself is basically pointing at itself. Wait a second. Previous tail. So if we had a previous tail, like 5, if 5 was our previous tail, 5 was our previous tail, it would be 5 that is now pointing to 6. And yeah, that is correct. And then after doing all of these, we will want to make sure that current tail dot next after getting out of this loop, we will want to make sure that current tail dot next is null, and then we will want to basically attach these heads and tails together. So we will say that current head dot next points to current tail. That should work. Let's hope that works. All right. Yeah, I think that's it. I think this is our whole function over here. And all we have to do is to pass it a node, and all we have to do is to pass it a node and an integer. So let's call it and see what we get. So I'm going to call the results that we get var result, and I'm going to call that function, which is partition, and I'm going to pass it a node, which will be our head, and I'm going to have 5 to be our partition in this case, and I'm going to console log the result. And let's cross our fingers and run this and hope for the best. All right. So we saw a hint of that here, right? In line 18. Is it pointing to that one? Main line 27 and then 43. Line 27. Alright, so at this point I would say let's just do this and not have to deal and don't deal with that anymore, and let's run it again. We are close actually, so maybe we don't need to do this. We can just say result If it's a linked list node, it should have print. Why doesn't it have print? We had print here, right? Yeah, we had print there. So, oh, okay, sorry. So we have to call our class and then call print and then pass it the result and then rerun this function. Okay. So what's happening here? Current head dot next. So let's just print out that. Two. Okay, interesting. Okay, so let's walk through this function and see what it actually does. So we're going to start with 2. 2 is so our head is the node 2 and our partition is 5, and we are going to start traversing through this list. Okay, so we pass 2 to this while loop, and 2 is our current node, right? So current node is assigned to head, which is 2. So while 2 is not null, so the nodes will not be null until we reach the very end after the last node. So we won't worry about line 15 anymore. So if the data of the current node was less than partition, so which in this case it is, current head will be assigned to current node. So current head is now assigned to current node. So that means that we are assigning that to current head, and then head is now pointing to null. What? Sorry. Current head dot next is previous head. So if we had a previous head, which in this case we don't, which is null, that would point to that. So and then previous head would be current head. Now let's go to the next element, 5. So for 5 is greater than, let's actually change that to be 3 so that we go over this case at least once. So 3. So 2 is both our current node and current head and previous head, and it's pointing to null, right? So if I come over here and I can maybe write it down. So we have 2 and it's pointing to null, and it's our current head and previous head. Okay, now let's go to the next node, node 3. Now 3 is less than partition. So what it does is that it says, so 3 is our current head. So here we have 3, which will now be our current head. And current head should point to the previous head, which is now still this node. So this points to this. And then previous head should be current head. So we will move this to here as well, right? So that's what should have happened. Now let's move to the next node. Next node is 8. 8 goes to the else block. Now inside the else block, what we do is that we assign the current node's data, which is 8, to current tail's data. So current tail's data should now be should now be 8, right? So current tail's data is now 8. So let's write it down here. Current tail is 8. It's not pointing to anything yet. And previous tail dot next would point to current tail. So nothing, which is null, so I'm going to write null again, is pointing to 8. And that previous tail, which was nothing, is now our current node. Now let's go to the next one. 3 is less than that, so what happens is that 3 will become our new current head. So 3 is our new current head, and it will point to a previous head. So here, previous head, and it will assign previous head to 3, right? Okay. The next element is 5. 5 goes to else block, and current tail.data would be assigned to current node.data. So 5 comes here, and it will be current tail, and previous tail dot next is current tail. So this dot next is this. Now previous tail will be current tail. Previous tail would be current tail. So like that. And then 6. So for 6, current tail data would be current node data. So 6 would be current tail data. And then previous tail would point to current tail, and then previous tail would become the current tail. So like that. And after this, we are saying current node, we are going to the next node. 4 is less than 5. Now 4 will become the new current head, and it will become the new current head, and it will point to the previous head. So it will point to the previous head, and the previous head will now be assigned to the current head. So we should get 2 linked lists like this. So at this point, I'm curious to see whether we actually have those 2 linked lists. So I'm going to print them out. Linked list node dot print, and I'm going to print current head and current. Actually, I can't print out current tail, and that's unfortunate, but let's first print out current head, and we are basically doing that. So why aren't we seeing current head doing its work correctly? Maybe we can just print out current head and current head dot next. Print. Print. And previous head. So now let's just concern ourselves with fixing head first, and then we will go to tail. So head at first iteration at first. So we are only going to this while loop only once. Why is that? We are only going to this while loop once. We are not changing the value of current node. Let's print out instead of these prints. Let's print out the current node and see what we get. Or let's just say current node.data. Right? Let's see how many times we are actually running this function. And let's just comment out that print as well. So if we run this, we are only going to this function once. And let's also see what's inside the next node after we are done with our if-else statements. Current node.next.data. So what do we have there? We have no. We have no. And we passed it node 1, right? Yeah, we passed it node 1. So current node is created off of head. What happens if I print out the current node here? Does it have the whole chain? Yeah, it does. So at what point did we override the next node of our current node? Oh. So 2 runs through this block. The first node runs through this block. And these are all objects. So we are, when we make a copy like this off of an object, we are basically, when we update the pointer of that copied object to previous node, previous head, which is null, we are basically modifying the original object. And that original object is now pointing to null. So what is the workaround for that? Maybe we really want to create a new linked list node, right? We will probably want to do that. So yeah, maybe we have to say, this is a new linked list node, or just like that, a new linked list node off of the data from this node, and we will define its pointer there. Okay, how about this one here? If you want to say this is also a new linked list node and it's created off of the data of this. So what happens if I run this now? Current tail. So 2, 3, 3, 8, 8. These are all, these, or sorry, 2, 3. 238, and we will jump out of the function at 8. And why is that? So 8. Over here says line 26, which is here. Cannot assign field next because previous tail is null. So you would want to say that, and for this one as well. Maybe that'll fix the problem. So yeah, we are now able to successfully go through the rest of the linked list. So now let me make sure that if I do this, if I instantiate these off of a new linked list node, it wouldn't break anything. And I don't get it why this is redundant. I can't understand that, so we'll just forget about it. So yeah, that doesn't cause any problems. So now we are able to go through the all the nodes probably, hopefully. And we can get rid of these print statements. Now let's see what we get when you print our head over here. So let's run this again. 43320. 0. I don't know where that 0 came from, but that's interesting. That probably came from current tail, right? Did we set current tail anywhere to 0? I don't think so. I don't know how that got to 0. Right, so we have that part covered. Now it's time to merge these two linked lists, so 4332, right, with this part. But how are we going to remember what was the head of this linked list? Well, we know what the beginning of this was, and we know what the end of this is, so maybe we should swap the algorithms of these two, right? So maybe I would have to say, so this part doesn't matter. Maybe I just have to say this. And I'm saying swapping these two because if I use this algorithm here, I would be able to have the end of this. And if I used this algorithm here, I would be able to have the beginning of this. But that would again cause some other problems because our we will lose reference of our head, and that would become troublesome later down the road. So do we really need previous tail? Previous tail dot next is the current tail. Can we just say current tail dot next is is or that we have a new linked list node over here. Just saying that we have a new linked list node and set its next node. So this is the next node, right? And set its next node to be that one. Can't we just say that and just have the previous node as the current tail as this one? Yeah, we can say that. And what is our current tail? It's null. So we will just assign this to our current tail. Right? And then what we have to do is to just do that. Is this now working? Yeah. Oh no. We have 8 here. 4, 6. Oh, okay. So we are... Okay. So we were able to get all of these as well. So 8, 5, 6, but in reverse order, 6, 5, 8. Now let's see if we can do the same thing for current head. So current head is so it will be a new linked list node, and it will be created off of the data. And it will point to the previous current head, which is null. And so if this is the case, if we want to do that, then we don't need all of those. And instead of returning, maybe I can call these merge head and merge tail. And then here I can say add another if statement. If okay, I can for storing the first head here, I can create another linked list node and call it result head, and set it to null. And if result head was null, only then run this line and assign result head to merge head. Okay? And return result head. So if there is nothing assigned to result head yet, assign it to merge head. So now let's run it again. Oh god, 2, 0. So let's print out our merge head and merge tail. So this is our merge head and this is our merge tail. Yeah. And this is a result of merging those in. So merge head and merge tail are created correctly. And let's now print out the result of result head. So result head should be 4. I expect that to be 4. Result head dot data. So yeah, that's the issue. We're not returning the correct item. So result head at first iteration is null, and result head is assigned merge head. What happens after that? So if result head is not null anymore, I expect it to not get any further values. So let's have these back. So when it's assigned 2, it's actually getting assigned something each time, or that we are creating a new head each time and pointing that to merge head. And so this is merge head. So we are pointing it to previous merge head. Oh, so merge head itself is moving, right? Let's see. So merge head first is here, and it's pointing to the previous merge head, which is nothing, or I can assign these to null now, right? So if I print this again, okay, we can't do that. Alright, so we have this, and what happens is that first iteration merge head is, I think, 0, and then it's pointing to 0 and assigning the data as this. So we are moving back at each iteration. So yeah, we are appending to the beginning here, right? So we are appending to the beginning. So maybe this is the merge head, and this is the result head. Result head. And I'm going to say that there. No, not there. Result head. So what happens now? Sorry, this has to do that as well. Yeah, and this has to be initialized here. So what is H print statement? So merge head is currently nothing. Merge head is 0. And we don't want to do this. So we will not put anything here. Maybe I can put its data as null. I can't. So we have an issue here. merge head dot next is current head, is result head. Merge head here is result head. If, sorry, merge head is null. I think that was the problem. Oh no. So let's go back to the version that was just working, sort of. And result head is 2, which is pointing to 0. So all I want to do now is to say that here result head dot next, so this node over here dot next is that, and I want to say that merge head gets returned. So if I try that, this is our linked list. It's pointing to 0, which I think is, we can fix that pretty much easily. So merge tail so do we have any reference to the tail? Can I just not do this? I can't. So maybe I can say if merge tail existed, then write merge tail. Can I do that? No. So can I write that here? If merge tail was not null, then do this, like this. Else, just assign the new merge tail, and then I will get rid of this. Okay, merge tail. Does it throw an error? So no. So if, yeah, that's now working. So we will just have to rename some of these variables, but yeah, this is now working, and we have to do the same trick here for the head as well. So you can just do the cleanup yourself as well, but I will try to do the cleanup here if my battery doesn't die. So if merge head was not null, then do all of these. Right? And else, just grab all of these and move them here. And don't assign that as the next node. And for the result head, we want to say, and we are returning merge head, so we have to rename merge head. We have to use result head here instead of merge head. Yeah. So wherever we have that, we would call it result head. And let's see where we have actually that result head after this line. So the first occurrence is here, and the next occurrence is there and there. So these are the 3 spots. two on line 17 and one on line 25. So let's first rename all these merge heads to result head, or just real head, and then rename these as merge head and rename this to real head. Okay, so let's give it one more shot, and this should be it. So we are calling this function, passing it our first node, and setting the partition to be 5, and then printing the resulted linked list. And the resulted linked list is off of real head, which is initialized as null. All of these are initialized as null. And whenever we detect that we have not defined the real head, we will create a new linked list node, and otherwise we will create that linked list node and not pointed to anything. So you know what the code does, so it's pointing to the previous real head. So let's run this one more time. And hola. So here is our partition. So this is our right partition and this is our left partition, and it's working as expected. Let me know if you have any questions or if you have any other solutions to this problem, and I will see you in the next video. Thanks for watching.